do some cubic functions and have a look at cubic graphing of polynomials. So you can see here that it can be in the inflection form, which is written as fx equals d, which is the dilation, x minus h to the power of 3 plus k. So we've seen this before, of course, in power functions, all right, in quadratics, all right, and you'll see this a lot in all these types of graphs, okay, where h and k is the point of inflection, in other words, where the graph changes direction, all right. There are 3 cubic polynomial functions. So the first one where we've got our inflection point, okay, which again we can have a look on our CAS here, where we're just going to do this same sort of one. So I've got my there's my dilation, right, even though I haven't put it in that example that's on the page there, all right, to the power of cubed, right. So you can see that's where it goes. Now I can also fiddle around with that, and let's say if I make it +1, the inflection point gets raised, right? The CAS can allow you to analyze the graph and come up with the inflection point. And there's my inflection point, right? And hence I can even change this, right? And it will show my change of the inflection point, okay? So depending on, of course, my equation, right, and where my inflection point is, right, the shape of the graph doesn't change, okay, but the inflection point does, because it depends on the values that I have is my h and k, right? So of course, right, depending on what happens, I can do analyze graph and get back the inflection point. There's my inflection point. If I don't know the x-intercept, I can also find out the x-intercept by analyzing the graph and having it for 0. There's my intersection point. All right. But of course, no matter what I do, I still find that inflection point. I still have to find where the basically x-intercept is, right? So you can see here that it's got the inflection point, but it also has my x-intercept, right? So it's quite easy to do this on your CAS, right? Plus we have other forms of cubics, right? So we've got a form where one might be a quadratic and then a linear function, linear factor, okay? And then we might have one where it's 3 linear factors, okay? So depending on, what form it takes, okay, might depend on if I've got a quadratic as well as a linear factor, or 3 linear factors, okay? In other words, 3 x-intercept points. So let's have a quick look at those, right? And we'll just do control new graph, just so it's a little bit easier. So let's do the first example here. So -3 all squared, right, times x minus 1. And there's my graph. Now, of course, depending on what the dilation is, and if I go back to the first one, if I change my dilation here from 1 to 2, right, it slightly goes up, right? So it gets basically steeper, right? Same as like when we do a quadratic, right? So the higher the dilation, the steeper it is. If I change it to 1/2, right, the wider it gets. In other words, the distance from the y-axis gets further apart, okay? Right, so it just depends on our dilation, right? Also, of course, if it's negative, it changes direction, and the turning point, because I haven't done anything for the inflection point here, right? Okay, then the inflection point still happens, right? But of course, because it's a negative one, now it goes in the opposite direction. So that's what effect the dilation has, right, on any of these sorts of graphs. And we've seen that before in our quadratic graphing, in our linear graphing. The same sort of effect happens, right, in all these polynomials, right, all these odd and even power functions, as well as all the other power functions that we'll look at. Truncus, hyperbolas, all of them, right? But let's stick to cubics, right? So I've got my cubic here, okay, and this has got a quadratic in it, and then a linear. There's my quadratic, and then a linear factor, right? So what I can do, of course, I can analyze graph. I can go to maximum, and I can go over to the maximum, and it will give me the turning point, right? Same as if I do analyze graph and do minimum. Oops, that was the maximum again. Okay, get out of that. Menu, analyze graph, minimum, right? And then just go over to that part of the graph. It'll tell me what the turning point is. But I already knew that because that's what that basically quadratic tells me, is it touches the x-axis at 3, right, and then passes through 1 as my other linear factor, or my other x-intercept. Okay, each of the examples here on this page shows that as x approaches infinity, positive infinity, that the graph increasing, right? So as we approach positive infinity, x, positive infinity, it increases, right? So it's increasing, okay? Except for this little bit here, right? Same with negative infinity. So as it approaches negative infinity, right? Negative infinity this way, okay, it's decreasing. That's what happens when we're doing normal graphs, right? Positive, negative, all right? A cubic polynomial expressed in the form of d, x minus r, x minus s, and x minus t, in other words, 3 linear factors, gives me 3 x-intercepts, r0, s0, and t0, all right? So 1, 2, or 3 solutions to the equation, all right? We have to factorize. In other words, we have to find linear factors by using either factor theorem, rational root theorem, quadratic formula, all those sort of methods that we've been using before, we have to use to basically graph any of these sorts of things. So if we have a look at the next sort of example, so grab another graph, and let's do the next example, x minus 3, x minus 1, x minus 5. There's my graph. I can see where they go. I can also analyze the graph and go 0, and it'll tell me all the x-intercepts, and of course we already know that because we've got it in the linear factor form anyway, so I already know that. We can then find, of course, analyze graph and do the maximum, and there's my maximum. All right, I can even do analyze graph, and if I try and do inflection point, it doesn't do anything, right? Because there's no inflection point. They're considered turning points, right? When it's not in the normal form, right? Or the base form of a cubic, right? So that's why we have to do these sorts of things so we can see where the turning points are, right? Same with if we do analyze graph and 0, we can find the x-intercepts. Alright, analyze graph, 0, and there's my 3 x-intercepts. But I already knew that because I factorized it. Alright, it's already in the linear factors. Alright, so I already knew where the factorized points are. Alright, so you can see how to graph this, right, on our CAS, and how to use the CAS to find different values depending on what the question's asking. Okay, and of course we'll need to do this by hand, so we'll do that in the next video.